Hi there, and welcome to Raylene Math. In this video on vectors in the plane, we will look at families of vectors that are parallel to vector v. Because a vector can begin anywhere, we're going to start at the origin, 0, 0, and then vector v tells us to move 2 spaces to the left and 6 spaces up from the rectangular components. The vector is a directed line segment, but we can also draw a right triangle by dropping a vertical line down to the horizontal x-axis. Then when we want to come up with the polar components, we want the magnitude and the direction. What we really want to know is the length of this hypotenuse for the magnitude. So the magnitude of vector v can be found using Pythagorean theorem. The square root of the horizontal component squared plus the vertical component squared. But those are really just the rise and the run values, or the directed base and the directed height. So the directed base is -2, meaning 2 spaces to the left, and the directed height, or the rise, is 6. So Pythagorean theorem gives us the square root of 40, and the square root of 40 we can simplify to 2 times the square root of 10. Next we want to come up with the angle in standard position, and so we measure from the positive side of the x-axis in a counterclockwise direction for positive. But in order to do this, we have to come up with a quadrant 2 angle, so we first come up with the reference angle, which is an acute angle between 0 and 90 degrees. And for this we know that the tangent of the angle, in particular the reference angle, is the opposite over the adjacent. But in this case we have the reference angle is a quadrant 1 sized angle, so the ratio has to become a positive. So we take the absolute value of the y component or vertical component of the vector divided by the horizontal component for the absolute value of the rise over the run. This is equal to the absolute value of a positive 6 over -2, which is equal to the absolute value of -3, or 3. And then to come up with the reference angle, we can apply the tan inverse to isolate for theta reference. This puts the angle of the vector, which I can specify by saying a quadrant 2 sized angle, is given by pi, 180 degrees, or pi radians, minus the reference angle. And so we get pi minus tan inverse of 3 for the actual angle in standard position. And so we can write the vector using angled brackets for the polar form to give the magnitude of 2 root 10 and the angle of pi minus tan inverse of 3. Part B is asking us to write an equation representing the family of lines that are parallel to vector v. We can write the equation of a line in many forms, but let's use the slope-intercept form or the function form, depending on what parameters you want to use for the slope and the y-intercept. There are lots of choices. What we really notice about having a family of lines is that we're talking about lines that are parallel. Let's get rid of that and let's copy the vector that we have. And if we scale that vector and put an arrow on the other end, we've created a line that is parallel. And so because it's parallel, we can translate it to any point we like, any starting y-intercept, and we see that we won't need to necessarily know the value of the y-intercept, b or c, or whatever we call it. But what it does have in common with the original vector is that it has the same rise and the same run, and so the slope has to be the same. So we know that the slope of the vector will be the slope of the line, and that's equal to the rise over the run, which is equal to 6 over -2, which equals -3. And so one equation that represents all of the lines that are parallel to this vector is another way of saying write the equation of a line that has a slope of -3. And so we are looking for the equation y equals -3x plus b, where b is any real constant. Part C asks, how is the slope of the line related to the angle of inclination of the line? Well, we found the line by taking the vector, which went 2 spaces to the left and 6 spaces up, creating a rise of 6 over a run of -2. So the slope is equal to the rise divided by the run, which is the same as the vertical component vy divided by the horizontal component of the vector vx, which is equal to the opposite to the angle theta divided by the adjacent of the angle theta, which is the tangent of the angle theta. Furthermore, we were given that the angle for the vector was pi minus tan inverse of 3. And so if we work out the tangent of theta, we get the tangent of pi minus tan inverse of 3. And if we use our trig identity, we can expand the tangent of a difference as the tangent of the first angle minus the tangent of the second angle divided by 1 plus the tangent of the first times the tangent of the second angle. And we can check this on a computer. Here I'm using TI Inspire, and we can work out the tangent of pi minus tan inverse of 3. And the slope is going to be the value -3. And that actually is our slope value that we had when we had a rise of 6 and a run of -2. So the slope of the line, m, is equal to the tangent of the angle of inclination, theta. That's the relationship we're looking for. In part D, we're talking about determining the distance between any pair of initial and terminal points on the vector v. Now vector v, of course, hasn't been scaled, and so there is a specific fixed distance that we are talking about. But we recall that we can translate this vector to begin and end at any initial and terminal points, and so this distance is nothing more than the magnitude of the vector, which we found by Pythagorean theorem using the rise and the run, or the horizontal and vertical components, to be 2 times the square root of 20. So really these questions are just reminding us to think about vectors in terms of things we already know: rise, run, slope of a line, opposites, and hypotenuses. In part E, we want to come up with all unit vectors that are first of all parallel to vector v. So we recall our vector v has a magnitude of 2 square root 10, and so we can put the vector v in rectangular or standard vector form, or we can put it into polar form. And what we want to do is to scale that vector, or change its length, to be a vector of length 1. And so if we imagine the first vector has a length of 2 square root 10, this smaller vector, if we have a ruler, we could measure it and say it has a vector length of 1. And so what we're doing is we're considering again a right triangle, and we are changing the hypotenuse length by a scale factor. So we are choosing a scale factor of less than 1, in fact of 1 over 2 square root of 10. So we are going to take the vector v and divide it by its magnitude to get a vector of length 1, which we use this unit vector notation, v hat. So we are going to take this scale factor and multiply it by both the horizontal and vertical components. This should say 6 here. And when we do that, we get -2 over 2 square root 10, which will be -1 over the square root of 10 I hat, and then 6 and the 2 reduce to give us +3 over the square root of 10 number of j hats. This will guarantee that we have a magnitude or a vector length of 1. And we can do that quickly to check. The magnitude of vector v is going to be the square root of -1 over the square root of 10 all squared, plus 3 over the square root of 10 all squared, which gives us the square root of 1/10 plus 9/10, and the square root of 10/10 is the square root of 1, which is equal to 1. And so we have the desired magnitude. Another way we could do this is to take the polar form and to divide it by the magnitude. But of course that would not change the direction because we are not changing the rise and the run or the angle of inclination or the slope. And so a vector of magnitude 1 would have the same angle but a magnitude of 1. And so we could rewrite the vector v in polar form to say that the magnitude is 1 but the angle is the same. Part B is, or the second part of E, is asking for a vector that is anti-parallel, and so what's happening in this case is we are changing the direction. Instead of going 2 spaces to the left, we want to go 2 spaces to the right, and we want to go 6 spaces down. And so to come up with an anti-parallel vector that is still a unit vector, we have to change the sign of both the horizontal and vertical components. And so our vector v anti-parallel we notice that we are asked to write it, we weren't specified the form, so I'm just going to write it in the standard vector form. So we have positive 1 over root 10 I hat minus 3 over root 10 j hat. And that's essentially the same as taking this vector of magnitude 1 and rotating it 180 degrees. So it still has a length of 1, but is now going to the right and down. In the third part of this question, we are asked to come up with all unit vectors that are orthogonal or perpendicular to vector v. Vector v has a certain rise and a certain run, and we can draw a line through that vector to make it a little bit more familiar to us. That vector then has a rise of 6 and a run of negative 2. But the line also has a run of positive 2 and a rise of negative 6. So we can calculate the slope of this line by taking the rise over the run, either to be positive 6 over negative 2 or negative 6 over positive 2. Either way, we get a fraction of negative 3. We can write negative 3 over 1 if we like. In fact, we can scale this fraction any way we like. We can scale it by multiplying by 1 in the form of anything over itself. And if we do this with the fraction of 1 over root 10, we can see that the slope is equivalently negative 3 over the square root 10 divided by positive 1 over the square root 10. And this indeed gave us the rise and the run that we just saw previously in the antiparallel unit vector. Those rise and run values then correspond to the v antiparallel hat that we saw already, and the original v hat was in the same direction, not rotated 180 degrees, and would have had a slope value of positive 3 over root 10 divided by negative 1 over root 10. And so we can see if we want to come up with a perpendicular line that we have to come up with the negative reciprocal slope. And so for here we have that m perpendicular is going to change the sign overall. So instead of being a negative overall, it will be positive. So we can either have positive divided by positive, or we could have negative divided by negative. And not only do we change the sign of the slope, but we also change the rise and the run, swapping them. So instead of having 1 over root 10 in the denominator, we have 1 over root 10 in the numerator, and vice versa for the 3 over root 10. And so this swapping of rise and run from one line to a perpendicular line is what we can use to build our unit orthogonal vectors. We will get 2 of them. We will get one here in red, which is v hat perpendicular number 1. And we have the right and up is going to be the positive delta y and delta x. Making sure to take the delta x first, we have 3 over square root 10 I hat plus 1 over the square root of 10 j hat. The second vector in green will be v hat perpendicular number 2, and we can take the negative 3 over root 10 as the x component, or the coefficient of the I hat, and then negative 1 over root 10 as the coefficient of the j hat. And there we have 2 different unit orthogonal vectors to vector v. Part F asks us to determine all vectors that are parallel to vector v in standard notation. We recall that our vector v was given by negative 2 I hat plus 6 j hat, which gives us a right triangle with a directed base of negative 2 and a directed height of positive 6. When we are interested in coming up with a vector or a line that is parallel, the key ingredient that we're looking for is to find the same slope or the same angle of inclination. So if we do that, what we're really talking about is scaling a triangle. So I can take that hypotenuse, maybe make it a bit smaller, and I can scale it to any length I like, and I know as long as I have a constant horizontal and vertical scale factor, meaning the same for the base and for the height, that I'm going to create another right triangle where all 3 angles are the same. And so if I take a scale factor from the small blue triangle, and it doesn't have to be from small to big, but in this case we have a smaller blue triangle to the bigger red triangle, we often use k as the scale factor, but we might use any letter we like. And I'm going to choose t here, which often represents time in physics. And therefore our new red vector is going to be a scale of t times v, which gives us a horizontal component of negative 2t, and that's the number of I hats, and a vertical component of 6t, and that's the number of j hats that we have. And so we can see here, if we are taking the slope of the blue vector, we take the rise over the run, and the rise is 6 divided by negative 2 gives us negative 3. Similarly, the slope of the red vector is going to be its rise of 6t divided by its run of negative 2t. And because we have a common factor, because of the constant scale factor for both base and height, we still get 6 over negative 2, which is equal to negative 3. Therefore, we have parallel red and blue lines, and we have parallel red and blue vectors. So, by similar triangles, we were able to come up with one vector which is actually an infinite number of vectors as long as t is not 0, because we can't divide by 0 down here. And this single vector represents a family of all vectors that are parallel to the given vector. In part G, we are asked to write a vector equation for all of the lines that pass through a point h, k and that are parallel to vector v. So vector v we found to be negative 2i hat plus 6j hat, which indicated that we had a change in x of delta x equal to negative 2 and a change in y of positive 6. But then we scaled that vector by multiplying both the base and the height by some scale factor. We called it t. And so our new vector describes a more general change in x of negative 2t and a more general change in y of 6t. So now that we have from an initial point of 0, 0 to some final point negative 2t, 6t, we know what the delta x and the delta y values are. We want to take it one step further though, and not just start at the initial point of 0, 0, but to translate that vector to start at any initial point that we are going to call h, k. So if we copy this vector and we paste it, we know that we can translate it without changing the vector. And so if we make this new vector start at a point, let's call it h, k, then we can actually come up with the final coordinates of the point and describe the line that we want. But first we need to recall that the definition of a change in something is the final value minus the initial value, and if we rearrange we can see that the final quantity is equal to the initial quantity plus the change. And so the change in x we can rearrange from being x final minus x initial to get that the x final, or the x as a function of some time, is equal to the x initial plus the change in x. And the x initial that we are dealing with is the coordinate h. And the change in x is called negative 2t for any scaled value of the original blue vector. Similarly, the y coordinate of the final point, which is y after some amount of time, is given by the y initial plus the change in y. This is k plus 6t. So we have the x coordinate for a point on the line is a function of time, and the y coordinate for the corresponding point on the line is given by a function of time. And so the line that we have is not just the vector, but it goes in both directions. And any point on the line will be given by x final, y final, or we might just refer to it as x, y. When we put all of this together, we get that the equation of the line, which might be the line L, not just the purple vector, but the entire line, is given by some function of time, and because it's got two components, a horizontal and a vertical, we use vector notation to represent the equation of the line. For the horizontal component then, we have h minus 2t, and the vertical component is k plus 6t. We can also write the equation of that line in Cartesian notation using point-slope form, where we would say y minus the y coordinate is equal to the slope, in this case 6t divided by negative 2t simplifies to negative 3, and then we multiply by x minus the x coordinate, which is called h. This is one way in a scalar or Cartesian form to write this same equation given by this vector format. And there you have a vector function which describes the equation of a line in the plane passing through a point and parallel to a given vector.